the most valuable resource we have, critical for the human well-being and the sustainability of our planet. Water will determine how economic development, human health and environmental sustainability will be achieved. Cities, industry, agriculture and nature all compete for ever more scarce water resources. Managing these competing demands and delivering solutions to secure our water future is an unprecedented challenge. Around the world, water professionals are managing water on a daily basis, providing safe drinking water and sanitation, and protecting water resources. The International Water Association is the global network of water professionals working on the most pressing water issues. We bring people together to share knowledge, experience and know-how, and find new ways to safeguard and deliver water supplies for the future. We connect scientists, practitioners and communities so that pioneering research can underpin new solutions. We foster technological innovation, support sustainability and drive best practice through international frameworks and standards. Inspiring change to deliver a better water future for all.
Good morning, good afternoon, good evening to all of the participants. I'm Professor Hu Zhangyong from National University of Singapore. Welcome you to IWA Webinar on the micropollutant removal in water reclamation. And this webinar is jointly organized by IWA Assessment and Control of Hazardous Substances in Water Specialist Group, as well as IWA Water Reuse Specialist Group. Everybody know that before I start some introduction about this webinar, there's a housekeeping rules. This webinar will be recorded and made available on demand on the IWA Connect Plus platform and IWA Network website with presentation slides and other information. The speakers are responsible for securing copyright permission for any work that they will present in this webinar. The opinions, hypotheses, conclusions, or recommendations contained in the presentation and other materials are the sole responsibility of the speakers and do not necessarily reflect IWA opinion. At the below part of this screen, you are going to see a chat box, which you can use it for journal requests and for interactive activities. And beside it, there's a Q&A box, which you can use it for sending questions to the panelists. And we will answer all of them during the panel discussion. All right, this is IWA's webinar's agenda for today. But before I touch on the detailed arrangement, I would like to just say a few words in terms of the main objectives and the background of this webinar. Emerging organic contaminants has been a serious concern in water reclamation due to their potential health impact and have attracted a number of the attention from scientific committees in today's world. However, how to effectively control them in water reclamation, it is still lacking especially in the application in real situation. So today's IWA webinar will introduce the occurrence and behavior of emerging organic contaminants in water reclamation, their control measures, and application in water reclamation practice. It will equip the water professionals with the needed knowledge and skill sets to handle the challenges imposed by emerging organic contaminants in water reclamation. So here today, okay, you are going to have some welcome messages from me, and also followed by welcome messages from Joseph, who is from Quebec, Austria. And we will then have a number of the technical talks given by our speakers, including Professor Li Wenwei from China, Professor Haruka from Japan, Dr. Ghosh from Singapore, as well as Dr. Honor from Namibia. After their presentation, and then we're going to have Q&A panel discussion where the speakers and the moderators will gather together and we are going to address the audience questions and comments. And following that, I'm going to close up this webinar at the end. Okay, you can see today's moderators and the speakers for IWA webinar on the micropollutant removal in water reclamation. And myself, Professor Hu Zhangyong from National University of Singapore. I'm also the specialist group chair for the assessment and control of hazardous substances in water. And together with me, my co-moderator, Joseph, he's WABEX Director for Research and Development, and he's also the chair for the IWA Water Reuse Specialist Group. And we have a number of the speakers with us, and we are very honored to have them to come and share with us in today's IWA webinar. The first speaker is Professor Li Wenwei. Professor Li is professor from the University of Science and Technology of China, and he's also the IWA Assessment and Control of Hazardous Substances in Water Specialist Group Management Committee member. And he has a number of the research interests, which many include advanced nanomaterials for catalytic degradation of water pollutants and resource recovery. He has been the editor board member of ACS, ES, and T Water. He's also associate editor for Chemical Engineering Journal. And so this is Professor Li Wenwei, our first speaker. And I will continue to introduce another speaker of today's webinar session. That's Dr. Gosha. Okay, Dr. Gosha is an environmental consultant, AECOM Singapore, and his research interest focus on quite a number of the cutting-edge areas, including advanced oxidation process, control of antibiotic resistance, environmental microbiology in the aquatic systems, and so on. Dr. Gosha was a lecturer from the University of Asia Pacific, and also he was also senior lecturer from the East West University from Bangladesh. So now I pass on to Joseph for him to, my co-moderators, for him to introduce another of the two invited speakers of our today's webinar. Joseph, please.
Thank you, Zhangyong. Haruka is an assistant professor in Research Center for Environmental Quality Management at the Kyoto University, Japan. In addition, since last year, she has been a management committee member of the Water Reuse Specialist Group, representing Japan. Thomas has a PhD in chemistry, and he is the general manager of Wingok, the Windhoek Goreangab operating company, Namibia. Next slide, please.
Next slide. Okay.
Yes. Chang Yong, please.
Thank you, Joseph. Okay, so since this is a webinar jointly organized by two specialist group of IWA, so I will be, first of all, on behalf of this assessment and control of hazardous substances in water specialist group, because I'm also the chair of this specialist group, I'm going to give a very brief introduction about this specialist group and what are we doing, who are we, and what kind of topics we like to cover. So this specialist group belongs to IWA Water and Health Cluster. We focus on a number of the very interesting topics, like a novel analytical methods for micropollutants, bioassay to evaluate the toxicity and also any health impact of the micropollutants. We look into occurrence in water, sludge, and the contaminated soil and sediments for the micropollutants, and we study their fate and effects in the environment. We also, investigate removal efficiency in the water and wastewater treatment systems. And in fact, today you're going to hear a lot of talks, which is about micropollutants and their removal in different, treatment processes. And we also, definitely like to look into the risk assessment and regulatory development for micropollutants. So our specialist group act as a conduit for interaction, discussion, and exchange of experiences and knowledge on impacts and technological improvement for further advancement in this field. Basically is micropollutants, or we call emerging contaminants. So more information can be found in the IWA Connect Plus. Next slide, please. So you are able to see the recent events organized by our specialist groups in the past maybe 7 to 8 years. And you can see on top of the workshops and webinars we organized in the past few years. And we have also organized our brand new specialist group conferences. Okay, you can see the 2017, 2019, but due to COVID, we postponed a little bit. We have one in 2022 and last year, 2024 in National Taiwan University. And you can see a lot of activities going on for our specialist group. And do watch out our next events and also the next newsletter, and can find more information from the IWA Connect Plus for the activities of our specialist group. Next, please. Okay, I will invite Joseph.
Thank you, Chang Yong. Next slide, please. The Water Reuse Specialist Group is globally the leading forum in water reclamation and reuse, and is the largest specialist group of IWA. Our major aim is the implementation of safe water reuse practice through the promotion of successful water reuse projects and sharing of information via our international knowledge network, website, and conferences. For example, our 9th conference we organized in Windhoek, next slide please, in 2013. And today we will have a presentation from Windhoek, which is, as you know, very famous for direct portable reuse. The last conference we had in India, in Chennai 2 years ago, the next conference in March this year in Cape Town. And for the 2027 conference, we have received 6 proposals. The winner will be announced at Cape Town. Next slide, please. On the road to Chennai 2023, we organized 4 webinars. The recordings can be found on the IWA website. Next slide, please. On the road to Cape Town 2025, today we have the 3rd webinar. The last event we organized in December on water reuse and public engagement, a global look. Next, please. As mentioned, the next conference we will organize in the beautiful city of Cape Town, jointly with the Water Research Commission. And from 16 to 20 March, and I would like to cordially invite you to join this globally most important water reuse event. Next slide, please. I thank you for your attention. Next slide. Thank you.
Hey, thank you, Joseph, for a nice introduction about water reuse specialist group. And now we come to our first presentation, which is going to be given by Professor Li Wenwei from University of Science and Technology of China. Prof. Li, please.
Okay, thank you. Thank you, Professor Hu. I'm Wenwei Li from the University of Science and Technology of China, and it is my greatest honor to give this presentation here. My topic today is innovative heterogeneous catalytic technologies for selective oxidation of micropollutants. Chemical pollution, next slide, please. Chemical pollution of aquatic environment remains a global challenge of growing concerns. Since the micropollutants cannot be effectively eliminated by the conventional biological processes in the wastewater treatment plants, so the chemical treatment can be used as a possible supplement. Next, please. Okay, so one important option in this line is advanced oxidation, as Professor Hu has mentioned earlier. For example, in Fenton oxidation process, highly reactive radicals are generated to effectively destruct the pollutants molecules. However, this process requires intensive energy or chemical input and generate hazardous sludge, making it too costly for wastewater deep treatment. Next, please. One important reason for the high chemical consumption of Fenton process lies in the poor selectivity of the generated free radicals, which are prone to reaction with the natural organic matters and inorganic salt in the water rather than the micropollutants, because they have much lower concentrations. Therefore, excessive chemical dosage is needed to ensure sufficient removal of the pollutants. Recently, the selective oxidation process based on non-radical catalytic reactions have emerged as a promising alternative. In this process, non-radical active species are generated to selectively target at the micropollutants, thus enabling more efficient utilization of the oxidation power and much less chemical consumption for the wastewater treatment. So the question here is how to precisely regulate the non-radical catalytic process. Okay, next. So the key lies in the catalyst design. Over the past few years, our group have developed a series of transition metal oxide catalysts to facilitate selective oxidation of micropollutants through non-radical pathways. We choose transition metal oxides here because they are cheap and flexibly turnable in composition and the structure. Next slide. Firstly, we fabricated a spinner oxide catalyst with fine-tuned geometrical structure. This catalyst not only allows preferential absorption of pollutants and oxidants, but also can generate abundant surface-bound reactive species for direct oxidation of the pollutants. Therefore, the overall system changed from the bulk reaction to the surface reactions, and from the radical to non-radical catalytic processes. It exhibits high efficiency for removal of BPA as a model pollutant here, and had very low oxidant consumptions. In addition, the system showed only slight performance decline for treatment of real water samples, including the lake water and industrial wastewater. Next. Okay, we further immobilized the catalyst into the forms and loaded them into a fixed bed reactor for continuous flow operation in order to test its feasibility for practical application. Similarly, this system also exhibited good water treatment performance. However, we noticed that the catalyst showed obvious activity decline during the prolonged operation due to the accumulation of the organics on the catalyst surface. In addition, the limited pollution absorptibility of the catalyst also presents another challenge. Next, please. To further address this catalyst passivation issue, we proposed another strategy for the catalyst optimization, that is crystallinity engineering. Through partial amorphization treatment, the resulting metal oxide nanosheaths exist drastically enhance the ability for pollutant absorption. More importantly, the pollutants was efficiently degraded by both direct oxidation and by radical pathways without obvious catalyst passivation. Here, the radicals played an important role in further mineralization of the surface accumulated organics. Next, please. As a consequence, the system exhibited ultra-high activity oxidant ionization efficiency and stability for BPA removal, outperforming other metal-based catalysts. Impressively, no obvious activity decline was observed during 10 consecutive operating cycles. Next. Its feasibility for selective degradation of other electron-rich pollutants and for treatment of real water and wastewater was also demonstrated. Nevertheless, we found that for some pollutants, for example, phenol, their intermediates cannot be fully eluted off actually from the catalyst. We have further investigated this process, and the results show that these pollutants actually form polymers on the catalyst surface. Next. Okay, since the polymerization reactions are difficult to avoid in this system and proceed very fast, we think, why don't we utilize it as a new route for water pollution control, for the pollutant removal? Therefore, we developed a mental oxyhalide catalyst to intentionally trigger surface polymerization instead of avoid it. Therefore, we opened a new decontamination paradigm that differs fundamentally from the conventional AOPs. Instead of pursuing pollutant mineralization, our system here achieved rapid pollutant removal in a non-degradative manner. So next, please. So in this new paradigm, because we don't need to break the strong carbon-carbon bond, it requires only very low chemical or energy input. For example, the conventional heterogeneous Fenton process with the oxidant to pollutant ratio of 100, that means a high consumption of the oxidant, achieved only about 15% pollutant removal within 5 minutes. However, in comparison, our polymerization system achieved 1800 pollutant removal at an ultra-low oxidant to pollutant ratio. That is only 2. That means 88% reduction of the oxidant consumption. Importantly, no hazardous byproducts are left in the treated water. Next, please. So this unique surface polymerization route also rendered the catalytic system superior environmental robustness and stability for treating real waters. In addition, it showed better performance than the conventional Fenton process in water detoxifications. Next. Okay, we also demonstrated its feasibility for advanced treatment of wastewater treatment plants effluent by constructing a catalytic membrane system, and its capability for removal of several representative PBCPs was also demonstrated. Okay, next. Okay, so thank you. I would like to thank the the IWA and the founders for support our research, and also thank my colleagues and students for their outstanding works. And thank you all for your listening. Thank you.
Thank you, Prof. Lee, for a very nice presentation given by you. And I will ask our audience, if you have any questions, please send your question into Q&A box, and we are going to discuss later on during the panel discussion. So now I hand over to Joseph for Joseph to introduce next speaker. Joseph, please.
Yes, Haruka is talking about effects of functional groups of polyfluoroalkyl substances on their removal by nanofiltration. Haruka, please.
Thank you. Thank you for the kind introduction, Joseph. Good morning, good afternoon, or good evening, everyone. My name is Haruka Takeuchi from Kyoto University, Japan, and it is a great honor to be able to speak to you. Today, I'd like to introduce the removal characteristics of PFAS, polyfluoroalkyl substances, by submerged nanofiltration membrane system. Next slide, please. As we know, trace organic chemicals, in particular PFAS and PPCPs, are challenging contaminants that have caused increasing concern regarding their threat to safety, reclaimed water, and drinking water. To remove these contaminants, advanced water treatment processes have been developed, and membrane technologies, in particular nanofiltration, has attracted attention due to their removal performance and their relatively low energy consumption. Next slide, please. Membrane technologies can be classified into 4 groups depending on their pore size: microfiltration, ultrafiltration, nanofiltration, and reverse osmosis membranes. Among them, nanofiltration membranes with typical molecular weight cutoff of 150 to 2,000 grams per mole represent powerful separation technologies for the removal of trace organic chemicals. Next slide, please. The major removal mechanisms by NF membranes include size exclusion effect, electrostatic repulsion, and adsorption. Thus, chemical rejection by NF membranes can be estimated based on their physicochemical properties of chemicals. However, interestingly, many studies have found that P4 had higher rejection value than PFOS, even though P4 has smaller molecular weight than PFOS. So removal mechanisms underlying PFAS rejection by NF membranes are still unclear. Next, please. And the removal performance of NF membranes are influenced by the configuration of membrane element, as well as its operation conditions. Oh, please, yes. And conventional element is called spiral wound membrane, which is operated at pressurized condition to achieve high permeate flux condition. However, this type of element consumes a lot of energy and susceptible to membrane fouling. On the other hand, this study focused on submerged NF membrane process. Although this type of element should be operated at very low flux, such as 5 LMH, the low flux operation can reduce energy consumption and omit pre-treatment to mitigate membrane fouling. Besides, no pressure vessels are required for this system, which leads lower capital cost. However, its removal performance for PFAS and PPCPs hasn't been investigated so far. So the objective of this study was to clarify the factors that influence the removal of 9 PFAS during submerged NF treatment. We mainly focused on exploring the PFAS rejection mechanisms by extrapolating the rejection mechanisms of 46 PPCPs based on their physicochemical properties. Next, please. Here, lab-scale experiment was conducted to evaluate the rejection of PFAS and PPCPs by submerged NF membrane process. And flat-sheet NF membranes, NF270 from DuPont, was used in the study. The membrane element was submerged into a feed water and operated at relatively low flux conditions, such as 5 LMH. As feed water, we used UV-filtered damp water, which was packed with 9 PFAS or 46 ppCPs at specific concentrations. Next, please. As shown here, target compounds include 9 PFAS and 46 ppCPs with molecular weight ranging from 151 to 916 grams per mole. Based on their properties, they were classified into 4 categories. One is uncharged chemicals, negatively charged chemicals, positively charged, and sweet ion. As shown in the bottom, all over the 9 PFAS are categorized into negatively charged compounds. Next, please. When we have a look at functional group of the target PFAS, 5 of them have carboxylic acid, and 3 of them have sulfonate acid, and 1 compound has ethyl and carboxylic acid. All of these compounds are dissociated at neutral pH and have partial negative charge at the carboxylic acid or sulfonic acid groups. And we calculated the partial negative charge of each PFAS based on quantum chemical calculation, and we found that the carboxylic PFAS have stronger negative charge than sulfonic PFAS, as shown in the bottom of this table. Next, please. Then let's move on to results and discussion. These figures shows the removal rates of target compounds as function of molecular weight or minimum projection area, MPA. The upper 2 figures are for PFAS rejection and the lower ones for ppCPs rejection. Next, please. As shown in the upper figures, the rejection of selected PFAS increased from 71 to 94%, and as their molecular dimension increased. And the same trend was observed for ppCPs. And this result indicates that the size exclusion effect is one of the important removal mechanisms for PFAS and ppCPs. Next, please. Next, please. Then I'd like to talk about the effect of charge on their rejection. The blue plots represent the rejection for negatively charged compounds, and green plots for positively charged ones, and red plots are for uncharged chemicals. As you can see, negatively charged PFAS and ppCPs were rejected to a greater extent than uncharged or positively charged compounds. Since the NF membrane used in the study has negative charge on its surface, electrostatic repulsion between the membrane surface and compounds led their higher removal rates. The rejection of positively charged compounds were relatively low because these compounds are concentrated on the surface of membrane due to the electrostatic attraction force. And this tendency was in accordance with previous studies. And from this result, we can say that in addition to the size exclusion effect, electrostatic repulsion is essential for determining PFAS and ppCPs rejection. And when we, And when we further look at the PFAS rejection, carboxylic PFAS, PFCAs, were rejected to a greater extent than sulfonic PFAS, PFSAs. As mentioned before, PFCAs have stronger negative charge than PFSAs, so the higher negative charge of PFCAs can lead stronger electrostatic repulsion, which results in the higher rejection of these compounds. So partial charge of functional group is an important property that governs PFAS rejection by NF membranes. So understanding the negative charge of PFAS is very useful to predict their removal rates by NF membranes. Next, please. For conclusions. This study investigated the factors that affect the removal of 9 PFAS during submerged NF treatment. And PFAS rejection increased as their molecular dimension increased, which means size exclusion effect is an important removal mechanism. Besides, electrostatic repulsion is another important removal mechanism for PFAS removal. And the partial charge of functional group is an important property that governs PFAS removal by NF membranes. Okay, next please. And finally, I'd like to give my sincere acknowledgement to my collaborators from Nagasaki University, Japan. And thank you for your kind attention.
Thank you, Haruka, for this very interesting presentation. The next speaker will be introduced by Changyong. Thank you.
Thank you, Joseph. The next speaker is Dr. Shayak Gosha. Dr. Gosha is currently in AECOM Singapore as an environmental consultant, and he's going to talk about UV-based advanced oxidation process for emerging organic contaminants removal. Shayak, please.
Thank you, Prof. for giving me the opportunity to present in this webinar. And good afternoon and good morning, everyone. Today, I will discuss about the UV-based advanced oxidation process for the removal of emerging organic compound from the water. So first, we try to define what is advanced oxidation process. Advanced oxidation process are identified by the generation of highly reactive hydroxyl radicals and other radicals such as reactive chlorine species, sulfate radicals, etc. Now, the conventional chemical oxidants such as ozone, chlorine dioxide are not very effective in degrading the emerging contaminant such as micropollutant. On the other hand, the radicals generated from the AOPs are very effective in degrading biochemically or chemically persistent organic compounds. So therefore, AOP is a very potential and sustainable solution to degrade micropollutants in the water. The examples of AOPs include the UV photolysis of conventional oxidants such as hydrogen peroxide, ozone, and free chlorine and persulfate. Now I will discuss about UV chlorine as an example of advanced oxidation process and its applications and limitations during the degradation of different pollutants. So UV chlorine as an advanced oxidation process involved application of simultaneous application of UV and chlorine. Depending on the pH and depending on the wavelength, during this UV chlorine process, a different reaction system takes place and a number of radicals generated. The radical generations and the concentration of the radicals highly dependent on the pH because depending on the pH, the chlorine aqueous solution can produce hypochlorous acid or hypochlorite ion. Now, the question is why we will use the UV chlorine process. First of all, UV and chlorine both are widely employed in the water treatment plants. So it is it's a very sustainable solution to implement this UV chlorine process in the water treatment plants. Secondly, one of the most conventional and popular advanced oxidation process is the UV photolysis of hydrogen peroxide. This process produces the major radical is the hydroxyl radicals, while UV chlorine process produces, as I mentioned earlier, a different number of radicals such as hydroxyl radicals, chlorine radicals, dichloride radicals, chlorine monoxide radicals. Hydroxyl radical is a non-selective radicals where the RCS react with the electron-rich compounds. So having different types of radicals helps UV chlorine process to degrade a different types of micropollutants in the aquatic systems. Secondly, the efficiency of any advanced oxidation process are determined by two parameters. One is the molar absorption coefficient, another is the quantum yield. So the UV absorption coefficient for hypochlorous acid and hypochlorite ion are around 59 and 60 centimeter, while hydrogen peroxide has a very relatively low molar absorption coefficient, around 19.16 per mole per centimeter. Now, quantum yield is defined by the ratio of number of molecules decomposed to the number of photons absorbed. Now, the quantum yield for the hypochlorous acid and hypochlorite ion ranges from 1.9 to 1.5, while hydrogen peroxide has a very low photolysis quantum yield, which is around 0.5. And additionally, UV chlorine process shows less electron energies compared to the UV hydrogen peroxide process. The research shows that UV chlorine process consume 30 to 75% less electrical energy than the UV hydrogen peroxide process. So now, how these radicals formed in the UV chlorine process? So as I mentioned earlier, the formation of the radicals in the UV chlorine process depend on two factors. Now, one is the pH, another is the UV irradiated wavelength. So now the first, the pH. Depending on the pH, if the pH is less than 7, then the photolysis of hypochlorous acid become the dominant reaction to start with for the UV chlorine process. Now, if the pH is more than 7, then photolysis of hypochlorite ion become the dominant reaction system to start with the UV chlorine process. Now, for the wavelength, if you look at the figure at the top of the right-hand side, you can see that hypochlorous acid and hypochlorite ion showed a very distinct, different absorption spectrum. Hypochlorous acid shows a peak around 240 nanometer, while the hypochlorite ion shows a peak around 290 to 300 nanometers. For quantum yield, for both hypochlorous acid and hypochlorite ion, the quantum yield decreases with the increase in wavelength. So these two factors and with the pH, interaction between these three factors, the molarization coefficient, quantum yields, and the pH will determine the type of the radicals produced and their corresponding concentration. For example, for hydroxyl, the concentration of the hydroxyl radicals produced from the UV chlorine photolysis, UV photolysis of the chlorine, we can see that with increase in the pH, the concentration of the hydroxyl radical decreases. Because why? When with the increase of the pH, the photolysis of the hypochlorite ion become the major reactions, and this hypochlorite ion react with hydroxyl radicals around 4 times higher than the hypochlorous acid. So there will be more hydroxyl radicals will be scavenged by the hypochlorite ion at the higher pH. On the other hand, for chloromonoxide radicals, concentration of chloromonoxide radicals increases with increase in pH. It is due to the fact that the scavenging of hydroxyl radicals by hypochlorite ion will produce more chloromonoxide radicals. So increase in pH will produce more chloromonoxide radicals. Okay, so now we already discussed that the wavelength is an important factor to determine the efficiency of the UV chlorine process. That's why the selection of UV source is a very important step during the optimization of UV chlorine process. Conventional UV lamp, low pressure UV lamp, emits wavelengths at a specific wavelength, which is 254 nanometer. On the other hand, the new technology of UV LED can have the ability to emit wavelength at a very flexible wavelengths. And this UV LED is also environmentally friendly. It doesn't produce any mercury pollutions, and it's very energy efficient. Now we'll try to see some of the examples of the photolysis of UV chlorine to degrade the micropollutants. So one of the example is metoprolol, which is a very common beta blocker used for the cardiovascular diseases. If we look at the graph, we can see that the UV or chlorine was not able to degrade this micropollutant, where UV chlorine process was able to degrade efficiently. Even it showed 3.6 times higher degradation rate compared to the UV hydrogen peroxide process. if we look at the impact of the pH on the degradation rate, we can see that increasing the pH will reduce the degradation rate. It is because this study used the low pressure UV lamp at 254 nanometers. The molar absorption coefficient of hypochlorous acid and hypochlorite are very close, but the quantum yield of the hypochlorite chloride acid is higher than the hypochlorite ion. So the scavenging of the hydroxyl radicals by the hypochlorite ion causes the reduction of the degradation rate for this micropollutant at the application of the chlorine and low pressure UV lamp. So what will happen if we use a UV LED? So if we look at the impact of the wavelength, we can see that for other wavelengths other than the 254 nanometers, the degradation rate increases with the pH because at the higher wavelengths, the molar absorption coefficient of hypochlorite ion becomes around 12 times higher than the hypochlorous acid. So more photons are absorbed by the hypochlorite ion, and it produces more radicals and more radicals, and that's why the RCS become the dominant radicals to degrade the micropollutants. So that's why the degradation rate increases with the pH, which is contradicted to the low pressure UV lamp. So UV chlorine also has been applied to inactivate the chlorine-resistant bacteria, where both 265 chlorine or 285 chlorine showed synergistic effect compared to the standalone processes. The mechanism involved by the UV chlorine process is to production of the radicals, and these radicals attacks the cell membrane and then attack the DNA and cause the inactivation of the bacteria. One of the challenges of the application of the UV process is the reactivation of bacteria. The bacteria can repair its damage caused by the UV by the photoreactivation or dark repair. If we look at this slide, you can see that the photoreactivation was dominant for both chlorine and the UV at the lower dosages. But when during the UV chlorine process, even at the lower dosages, there is no reactivation was observed. If we look at the microscopic image of the bacteria cell membrane, we can see that the UV chlorine process degrade the bacterial cell to a great extent, which is hampered the production of the micromolecules such as proteins or enzymes. So as a result, the bacteria was unable to reactivate. So UV chlorine process also, now we'll see the application of the UV chlorine process to degrade the antibiotic resistance genes. So this study employ UV low pressure lamp and UV and the chlorine at the same time, and showed that the UV chlorine process showed synergistic effect compared to the standalone processes. And they found that the hydroxyl radical was the major radical to degrade the antibiotic resistance genes. It is due to the fact that hydroxyl radicals are non-selective radicals and can react very fast with the DNA, whereas the reactive chlorine species do not react very efficient to the DNA because they cannot react with the electron deficient compounds, and DNA is electron deficient compounds. Also, the electrostatics repulsion is another reason that the reactive chlorine species have negligible effect on the degradation of the ARGs. Now, the factors which affect the UV chlorine process are pH. As we also say, the pH can affect the type, nature of the radicals and their concentrations. Usually, the doses of chlorine, usually increasing the chlorine doses will produce more radicals, but higher chlorine doses can scavenge the radicals, so it can reduce the degradation of the pollutants. Carbonate or bicarbonate actually scavenge radicals, so it is also reduce the degradation efficiency of the UV chlorine process. For the organic matter can have impact in two ways. Organic matter, it can produce radicals during the UV photolysis, which will enhance the degradation. On the other hand, the organic matter can absorb UV light, and it can also scavenge the radicals, which actually reduce the degradation efficiency of the micropollutants. Now, formation of the disinfection byproducts is a very great concern during the application of the chemical disinfectants. Chemical disinfectants react with the dissolved organic matter to form these DPPs. These DPPs are very carcinogenic, and that's why US EPA has set a maximum concentration level for these DPPs. So during the UV chlorine process, the radicals first attack the organic compounds and produce some intermediates. These intermediates are very highly reactive, and then they can work as a precursor to produce the DPPs. So during the application of the UV chlorine process, at the initial times, there usually we can see an increase in the DPP concentration. However, if we increase the reaction times, these radicals can cause the dechlorination or mineralization of the DPPs. As a result, it can reduce the formation of the DPP. So in conclusion, we can see that UV chlorine process is a very effective advanced oxidation process to degrade the micropollutants with lower energy consumption and higher degradation efficiency. UV chlorine process provides synergistic effect to inactivate the bacteria virus. UV chlorine process is also very successful to depress the reactivation of the bacteria. We can also see the formation of radicals highly dependent on the pH and the wavelength. Chlorine doses and water matrix have a significant impact on the degradation of contaminants. The formation of potentially toxic DPP is still a major concern for the UV chlorine process. Extending the reaction time for the UV chlorine process may reduce the DPP formation compared to the chlorination alone. Thank you everyone. That's the end of my presentation.
Thank you, Shayal. Okay, I hand over to Joseph for your introduction of our next speaker.
Thank you, Chang Yong. Thomas will talk about contaminants of emerging concerns removal in a DPR, direct potable reuse facility in Windhoek. Thomas, please.
Thank you very much, Joseph, for the kind introduction, and good day to all of you. So this one is from real data from an operational side, which you can see on the slide. Actually, next slide, please. Quick overview. Next slide, please. So direct potable reuse was introduced in Windhoek in Namibia in October 1968. So we're in the 57th year now. It is the oldest facility in the world where direct potable reuse was actually purposely implemented. And the history actually dates by far back longer than only 68, because there were many years of test work, trial work, and then construction before the actual plant went into operation. And the first plant had initially a production capacity of 4,800 cubic meters a day, which was, then it resulted in 4 upgrades and changes of the plant. And in the late 90s, the plant had a production capacity of 14,400 cubic meters a day. At the same time, in the 90s, City of Windhoek decided to actually build a new plant, a new Goranga water reclamation plant, with a capacity of 21,000 cubic meters a day. This plant was commissioned between 2001 and 2002. And the private contractor, Wingok, was actually tasked after a tender process with the operation and maintenance of the plant. And Wingok is the shortcut for the Windhoek Goranga operating company, a joint venture of Veolia and Wabak. If we could go to the next slide, please. You see on the process overview, we have 2 possible sources of raw water. And maybe you saw it on the picture earlier, there's a dam, a smaller dam in the background. But since 2008, we solely take water from Gamam's water care works, the effluent treatment plant, activated sludge plant, and not from the dam anymore. Whereas we must say in the past, before 2008, the supplementation from the dam was a few percent, maybe ranging between 5 and 25%. And always the majority of raw water was from the effluent treatment plant. The process starts in that box where coagulation stands, first with pre-ozonation. Then we add ferric chloride, and we try to make enhanced coagulation. We can add a polymer should the floc not be sufficient for the flotation, but actually that's just a emergency backup, which we don't use. The water is then going through the dissolved air flotation, where we adjust the pH with sodium hydroxide afterwards and add a little bit of potassium permanganate to oxidize any residual manganese or manganese 2 and iron 2+, which then will eventually precipitate and be captured on the rapid gravity sand filtration, which actually is a dual media filter. And from there, the water goes into the main ozonation. Ozone is dosed 3 times at the beginning, after 1/3 and after 2/3 of the contact time, whereas the residual ozone concentration is measured before each dosing. After that, we go into biological activated carbon, followed by granular activated carbon, ultrafiltration, and only then we add chlorine and stabilize the water if need be with sodium hydroxide again. The process was designed according to the multi-barrier principle, which applies inside this process, but also outside. So for example, the raw water, the raw effluent entering the Gammam's water care works does not contain the water from the industries. So it's a real municipal effluent. And the final water, which is drinking water quality, of course, will be blended with other water sources and distributed throughout the city of Windhoek. Next, please. What is quite interesting, already in the first steps, which is the pre-ozonation and enhanced coagulation, and obviously the liquid solid removal was the DEF and the sand filtration. We see on some micropollutants already quite an interesting and high rate of removal. So I took 4 as indicators. Whereas with sulfametoxazole, we actually see like almost a 75% reduction. It's an antibiotic. Carbamazepine, which is an anti-epileptic, let's say, is reduced by 50%, similar to the benzotriazole 5-methyl-1H corrosion inhibitor, whereas we don't see a good removal rate. Well, it's still visible for acesulfam, a sweetener. So the pre-ozonation with a relatively low dosing of ozone compared to the main ozonation and the enhanced coagulation have actually a very visible effect on some CECs already, in addition to the typical liquid-solid separation. Next slide, please. What we see with the main ozonation, and as an indicator, I want to show you actually the formation of formaldehyde and acetaldehyde. Oh, and I want to put your focus on also always check the units. Okay, so the previous slide had nanograms per liter. Okay, so parts per trillion. Now we talk of micrograms per liter. So we actually get fairly little formaldehyde, acetaldehyde from the effluent treatment plant. But after the main ozonation, we have a dramatic increase of the two. And that is a very good indicator that actually our oxidation process of the larger organic molecules works extremely well. We do not see a huge, let's say, dissolved organic carbon or chemical oxygen demand or UV254 change through the main ozonation process, but we see a significant change in the composition. So what we get into the plant is obviously the non-biodegradable stuff. And that main ozonation transforms it into biodegradable molecules. And I think it's really obvious how well it works, and also how well the biological treatment followed by the main ozonation works again. So it's the removal rate is quite high. Well, there's obviously a polishing with the granular activated carbon filter, and what's obviously quite a nice effect of the biological filter, with the removal of the formaldehyde, acetaldehyde, we see no problems on chlorinated disinfection byproducts at the end when we add the chlorine. Okay, next slide again. Okay, just as a quick recap, again, we're now in the middle of the process. So the main ozonation biological activated carbon, granular activated carbon. Just to familiarize yourself quickly with this slide. Okay, next one. Again, so what we see here is a compilation of various, or again, those 4 parameters. We changed one to pyrimidone, which is again an anti-epileptic. And what's quite interesting, you see a huge variation of them throughout the years, but also throughout the different seasons of the year. And quite interestingly, pharmaceuticals are, well, we see it actually, the global availability, global supply chain issues. And when we do target-specific analysis, we also contact the local Ministry of Health, we contact pharmacies and see what's actually available, what is prescribed currently in the country. And as you see with pyrimidone, that one was stopped to be used, and we took it off the list and introduced some others. Just to say, it's a short list. We obviously have quite a lot of analysis we do. We look for aromatics, solvents, halogenated, non-halogenated, PCBs, pesticides, phthalates, benzotriazoles, pharmaceuticals, hormones, and a lot more. We do a lot, but I just took 4 on here. Next slide, please. Here again, no, yes. Already, well, after the GAC filtration, we actually see that all the CSCs are below detection limit. Typically, they are below detection limit after the main ozonation. And yeah, the process works. Next one. So the ozone BAC GAC process, maybe in comparison with the RO advanced oxidation, has proven itself really as a valid, sorry, I'm not saying the other one is not valid, but maybe they are 2 valid and 2 very useful process trains to actually implement DPR. And the area, the site requirements might then determine which one is actually the more applicable one of the 2. Obviously, as you see in the background, the plant, I'm obviously a big friend of the ozone BAC GAC process. What we did over the years, we always implemented new methods. We increased the number of compounds we analyzed for. And actually, some years ago, we started to looking into bioassays together with the chemical footprint analysis to overcome the limitations of the target-specific analysis. And well, as a teaser, as Dr. Lahnsteiner mentioned earlier, we are on the road to Cape Town. So maybe there's some more results presented on the bioassay chemical footprint, which we did over the last few years in Cape, and that will be March in Cape Town. Thank you very much.
Thank you, Thomas. Next slide. Yes, we start now with the discussion. I would like to ask the first question. It's, what about the oxidation products of the process? All the micropollutants going to CO2? No other sub-products are generated, question mark. Who is answering this? It was to Miss Professor Lee, but Zhang Yong, you...
Oh, no, I select this question to be answered live. So let's invite Professor Lee. Prof. Lee, would you like to provide some answers for this particular question, which is about your oxidation products in your AOP process?
Okay, sure. Thank you. So the answer is, I think, not all of them are mineralized, turned into carbon dioxide, but actually most of the organics are converted to some smaller molecules, like some organic acids. And some of them also depends on the catalytic process. Some of them, just like I have mentioned, were polymerized into the larger molecules. So this is different for different cases. Thank you.
Thank you. Thank you, Prof. Lee. I think there are another two more questions which is associated with your talk. Maybe I take this opportunity to ask you at the same time. So one question is whether any external oxidant need to be added in your system. Is any external oxidant like H2O2, that kind of oxidant, anything like that need to be added?
Yeah. I do add some H2O2, and in several cases we use the PMS as the oxidant. But in our other recent studies, we also use the air, oxygen from the air, because that means we don't need to input the external oxidant.
All right, that sounds very good, very clear. One more question, okay, still for Prof. Lee's part. Okay, there's one question asking, if you immobilize your photocatalyst onto a robust support, whether this is going to affect the photoactivity of your catalyst. Do you ever thought about anything, anything could be a little bit inhibitory like that?
Oh, actually, I did not mention for the catalyst this time, but actually I have do a work using immobilization of the catalyst onto a PVDF membrane. So we use the strategy first. We use some chemicals to soften the fibers, and then the fibers get stretched, and we immobilize the catalyst in. Then it become shrink and become hard again. Then it was firmly bonded onto the surface. So this work has not published yet.
Thanks for sharing. Thanks, Prof. Lee. Thanks again. Very nice, question answers for all the questions actually related to you. So I pass to Joseph, and you may like to ask other of our speakers.
Yes, a question to Thomas. Can you tell us the empty bed contact times of the BSC and GSC filtration processes?
10 and 20 minutes.
Okay, thank you. Another question to Thomas. In Ghana, we use the same technique process to remove dissolved iron in the water, but we realized that after the treated water is left for some time, you could visibly see that the iron has precipitated again. Do you also experience this? If you do, how do you make sure there is no residual iron in the treated water?
I'm not so sure whether if typically you would see that precipitation occurring after time could be manganese. So manganese 2 oxidizing to manganese dioxide, manganese 4 species, and that we actually control with the pH. So we ensure that the pH is well above 7.5, well, not too high, of course, but when we dose the permanganate after the dissolved air flotation, we ensure that the pH is sufficiently high to have a proper oxidation process by the permanganate.
Okay, thank you. Maybe a question to Mr. Gosch from Max Zimmermann. Thank you for your interesting presentation. In the applied context, the context of disinfection for water reuse and micropollutant removal, I would like to know if you have analyzed the differences in DPP formation and ecotoxicity when comparing disinfection by UV Cl2 versus chlorine disinfection alone.
Yeah, thanks for the questions. So as I was discussing at the last slides of my presentation, that the UV chlorine process, due to production of the very reactive radicals, at the beginning of the reactions, it can produce more DPP compared to the chlorination alone, because the hydroxyl radicals react with the organic matter and produce the organic intermediates, which are very reactive and to produce the DPPs. And that's why the ecotoxicity or genotoxicity was found higher at the initial stage of the UV chlorine reaction of the UV chlorine process, but extending the reaction time can reduce this DBP formation, also the ecotoxicity and genotoxicity, due to the fact that the hydroxyl radical is capable of dechlorination or the mineralization of these DPPs. But there is also discrepancies existed in different studies. So this is a very potential field to do more research and to understand more about this DPP formation at the under the UV chlorine process.
Okay.
Yes, Shayak, thanks
Thank
for
you.
doing this. And I'd like to add on one question which is also raised for Shayak. It's about wavelengths and the dosage of UV and dosage of the chlorine. Okay, how do they impact on the UV chlorine AOP process? Would you like to address on this particular question?
Yes,
Dosage of UV and chlorine as well as UV wavelengths.
Okay, so first I start with the wavelength. So the wavelength have two different impact. As I mentioned, the two factors, which is the quantum yield and other the molar absorption coefficients, are very important to determine the efficiency of a UV chlorine process. So if you look at our slides, you can see that the hypochlorous acid and hypochlorite ion has a very distinctive molar absorption spectrum. So around 290 nanometer, hypochlorite acid show the peak, and the hypochlorous acid showed around 240 nanometers. Also, the molar absorption coefficient at the higher wavelength is higher for the hypochlorite ion. So if you use the higher wavelength, then the photolysis of the hypochlorite ion may become the dominant reaction to start with. And also, increasing the wavelength, the quantum yield also decreases for both of the species. So, since this wavelengths determine which reaction will be becoming the dominant reaction to start with, this also have the impact on the which radicals will be the dominant radicals, which radicals will be the higher concentration. So second is chlorine doses. So usually, if you increase the oxidant dose,
can you make it short? Your answer.
Okay, sorry. Okay, so for the chlorine doses, increasing the chlorine doses will produce more radicals, but so cause more degradation of the micropollutants. But sometimes these higher chlorine doses can scavenge the radicals and reduce the degradation of micropollutants. And for the UV fluences, higher UV fluences will generate more protons, so theoretically should produce more radicals. But also every system has their own optimization, so you have to optimize your system to degrade your target micropollutant with respect to UV fluence.
Thank you very much, Shayak.
Maybe a last question. This would be to Haruka. Which type of nanofiltration you conducted, the dead end or cross flow, and what are the considerations for this?
In this experiment, we conducted a submerged NF membrane. So the flat sheet NF membrane is applied, and then the flat sheet membrane that consists of the membrane element, and they are submerged into the feed water. So this is a kind of dead end filtration, and the permeate samples are collected by suction filtration.
Thank you.
Okay, I think this is about the time for us to wrap up this panel discussion session, and let's move on to our closing session. So I would like to recommend this upcoming IWA webinars and events to all our participants today. And you can see we have webinars on innovative nature-based solution, and as well as a webinar on advanced nanotechnologies for water purification. So learn more about our future online events in this IWA network, in IWA Learn especially. And there's also a conference calling for submission now, and this is IWA Conference Water and Development, which is going to be in Thailand in the end of the year. So you still got the time to actually submit your abstract and prepare for it. And next slide, please. Yeah, and also consider joining IWA, because IWA is our network for water professionals. And if you join using this code, you will be getting 20% discount for a new membership. And please join before end of the year as well, and find more information from this IWA Connect website. And next slide, please. Okay, I would like to, as the co-moderator, together with my co-moderator Joseph, like to acknowledge IWA headquarters and IWA Assessment and Control of Hazardous Substances in Water Specialist Group and Management Committee, because our committee members are also supporting for this event. And also IWA Water Research Specialist Group and the Management Committee and member of that committee. And I'd like to thank all the speakers, invited speakers, for their very nice sharing and the materials and the knowledge they bring to this webinar. Definitely, we gain a lot from them. And thanks for audience. And I really appreciate we got more than 400 participants today, and we have quite a number of the questions. And you are very active and asking so many important, interesting questions. And later we will follow up with your question. Okay, you will get answers, definitely. And also toward the end, lastly, I'd like to showcase to you the 2 follow-up events, which are IWA conferences. Okay, Joseph already mentioned about Water Reuse Conference, which is in this March in Cape Town, in South Africa, right? And, I think you are probably ready to go because it's only 2 months away. Another one is IWA Micropollutant and Eco Hazard Conference, which is my specialist groups conference. Is going to be in June 2026 in Toronto, Canada. So you watch out for call for abstract. Okay, it's going to come out soon in this year, definitely. And then we are going to have a nice event in Canada, right, next year, middle of next year. So it's going to be a very nice place, nice weather. And definitely we will continue to talk about micropollutants in water reclamation, in other water environments, and in solids, and in sediments, and so on and so forth. So with that, I'd like to thank everybody again, and and wish you a very good evening, and also good day, and look forward to seeing you very soon in the IWA Water Reuse Conference or IWA Micropollutant and Eco Hazard Conference or other events. Thank you, everybody. Thanks to staying with us. Have a nice day, evening, whatever, and see you soon. Thank you, everyone, staying here, and Thomas, Shayok, Haruka, and also our IWA colleagues, and of course, most important person, Joseph. Thanks, everyone. Okay, we're going to end up here. Thank you.
Thank you.
Thank you. Thank you.
Thank
Thank
you.
you. I guess we can probably feel free to leave. There's a no after